So for this set of problems in relation to exam number 2, we're going to do parts D and E that were on that was on page 7 of exam 2, which asked us to evaluate or find the derivatives, or evaluate the following by finding the derivatives. So let's start off part D. So part D, we have y equals 3 to the power 1 minus 4x squared over cosecant of x to the power of 3. So first of all, when you have like these types of problems, what I like to do is just like look at them as a whole first in order to determine what kind of derivative we have to find. So in this case, we have to use the quotient rule in order to find the derivative of this expression. So the quotient rule is more something more like low d high minus high d low over low, which is very useful for me to remember, and thank you to Mr. E for that. But what this refers to, so low refers to the term here in the denominator. D high refers to the derivative of the term in the numerator, and then minus high, which just refers to like the original term in the numerator of the expression, and then the derivative of low, which refers to the derivative of the denominator, and then low, you're just taking the low term or the denominator and just like squaring it. So in this case, let's use the quotient rule and dissect this one by one. So low, we got to start off with low. So low is cosecant of x to the power x over 3. So in this case, we can just write cosecant of x over 3. There you go. And then times the derivative of high. So the high term here is 3 to the power 1 minus 4x squared. So we got to find the derivative of that and like add it onto here. So whenever you have a term that has like that has a function as an exponent, so like for example b to the x, the rule for that is always going to be ln of b times b to the x times the derivative of x, or x prime. I don't know, we can just like describe it as like that for these kinds of purposes. So taking this term, or taking this concept and applying it to the term here, so our base is 3 and rx is 1 minus 4x squared. So in this case, it'll just be ln of 3 times 3 to the power 1 minus 4x squared times the derivative of the exponent, which in this case 1 would just be 0 and 4 would just be 8x, or negative 8x for this matter. So this would be the d high. So it would be in this case cosecant of x over 3 times, or we could just write it as ln of 3 times 3 to the power of 1 over, or 1 minus 4x squared times negative 8x, and then minus. So now we just plug in the high term, or the numerator, which is just 3 to the power 1 minus 4x squared times the derivative of low. So now we got to find the derivative of the denominator, which is the cosecant x to the 3, or x over 3, sorry. So the derivative of cosecant is negative cosecant cotangent, or negative negative cosecant x cotangent x. So given that x in this instance is x minus x over 3, it would just be the derivative of the numerator, or the denominator would just be negative cosecant, oops, denominator, right? Negative cosecant of x over 3 times cotangent of x over 3. But the key here is that we must use the chain rule, since we have a trig function and we have a function inside of that trig function, or that trig derivative. So the chain rule, you first find the derivative of the trig and you leave the inside functions such as, or as the original, and then after you find that, you just multiply that by the derivative of the inside function, which is just, so it would just, we'd multiply the derivative of x over 3. So the derivative of x over 3, in this case, we can just use quotient rule again, so we'll just do low d high minus high d low. So we just do 3 times 1 over minus x times the derivative of low, which would just be 0 in this case, over low would just be 3 squared in this case. So that just should just give you 3 over 9, which just gives you 1 over 3. So 1 over 3 is going to be our derivative of the inside function. So we have that, so we just multiply that, so that we can just add it to this function right here. So it'll just be multiplying. Yeah, so we just multiply this, and then it would just, this whole thing would be all over low. So you would just take the denominator that we have and just square it. So you just have, in this case, cosecant squared of x over 3. So to get a better look at this, or rewrite it as a whole in order to understand what this would look like, we can just write it as cosecant of x over 3 times ln of 3 times 3 to the power of 4 minus, to the power of 1 minus 4x squared times negative 8x minus 3 to the power of 1 minus 4x squared again, and then times that to this. So it would just be, or in this instance it would just be plus, because you have two negatives multiplied together. So or not necessarily, you would have like, you would apply two negatives here, because it would be this minus, if you multiply the signs of both, it would just be positive. Or you can just like leave it as that and just like rewrite it in parentheses as like a negative cosecant of x over 3 cotangent x over 3 which was times 1/3. Okay, and then you have this whole numerator over cosecant squared of x minus 3. And like for these kinds of problems, you can just leave them as that. You don't necessarily have to like simplify it down even further. You can, but it's just like more complicated in this sense, so I just wouldn't recommend it to anybody. But yeah, that's how you do part D. And then for part E, again, as we talked about previously, you want to look at the expression as a whole first. So you have y equals ln of square root of x times tan inverse of sine x. So in this case, we can apply the product rule because we have two terms right here that are being multiplied together. So this would be u, this would be v, and then again, product rule will always be defined by u prime times v plus v prime times u. So in this case, to find the derivative or the prime u of ln of square root of x, this would just be 1 over square root of x times the derivative of the inside. So the derivative of the inside of square root of x, we can just like do it over here real quick. And again, like as I mentioned in previous videos, I like to rewrite this. So square root of x equals to x to the power 1/2, x to the power 1/2, and then I just like to use power rule in order to make it simpler for me. So it'll just be 1 over 2 times x to the power of negative 1/2, which just gives you 1 over 2 times square root of x. So we got the derivative, so we just do 1 over 2 square root of x, so which gives us the u prime in this case. And then now we just plug in v, like the original it has, so it would just be tan inverse of sine x in this case, plus now we gotta find the derivative of the v term here. So in this case, the derivative of tan inverse is always going to be 1 over 1 plus x squared. But keep in mind, since we have another function inside of the trig, we have to use chain rules. So in this case, we found the derivative of the trig. Now we gotta multiply that by the inside function, which in this case should just give you cosine of x. Yeah, that should be the derivative of v. So you would just do 1 over 1 plus x squared times cosine of x. Honestly, I would probably write like big parentheses around them just to like a way to like differentiate what terms what. So this would be v prime in this case times u, which should just be ln of square root of x. There's some terms here you can probably simplify, or you can like rewrite them together. Or you can just leave it as if you'd like. I mean, it's completely up to you. But honestly, you could probably rewrite this as I can just like rewrite it as 1 over square root of x. Or in this case, it would just probably be 2x, because you're combining these two together. So square root of x times square root of x is just like square root of x to the power of 2, because you're adding the powers together. So in that case, it cancels out the square root, so it would just be x. So it would just be 1 over 2x times tan inverse of sine x, plus, honestly, you can just like rewrite this as cosine of x over 1 plus x squared, and then times ln of square root of x. So this should give you the final answer, or the final derivative for this expression right here. So yeah, that's really all for it.